In this tutorial, we're going to take a look at a test review on Cartesian vectors. If you happen to be taking my course, my Calculus Vector course in the province of Ontario, Canada, this is a test for Unit 7. And of course, if you're also a student in Ontario using the McGraw-Hill textbook, this is Unit 7 because we use the same textbook. So first of all, some multiple choice in the first part. In question number 1, it says or asks, what are the coordinates of C if the vector CA is 5, negative 2, 4, and A is the point 3, 1, negative 2? Now, a little terminology before I get it very far here at all. I use square brackets to represent vectors, round brackets to represent points, so to help distinguish between them, because if you use the same terminology, you'd always have to be reading to a question. Is it a vector? Is it a point? So we know where the head of the vector is. We know that A is the point 3, 1, negative 2. Remember, you take the coordinates from the head of the vector and subtract the tails to get the components of the vector. So basically, if I take this 3 here, this x component of 3, and subtract, okay, so the x component of my other vector, of my other point, sorry, I should get 5. So that number would have to be negative 2. We take the y coordinate of 1 and subtract y, I should get this negative 2 here. And that would have to be 3. 1 minus 3 is negative 2, so the y coordinate would be 3. And the z coordinate now, negative 2 minus z equals the 4 here. Now, if we solve, we want to isolate for z, so I'll isolate the negative z first. Negative z, or z if you're an American, we would take the negative 2 and over and add it to the 4, so that'd be 6. So negative z equals 6, so z would be negative 6. And so negative 2, 3, negative 6 that's the point listed in E, so that's why E is the correct answer. On to question number 2. Which of the following vectors does not have a magnitude of root 29? Well, the magnitude of a vector formula, we take the components and square them and add them and take the square root. So we're really looking for the number, the vector here, that the x component squared plus y component squared plus the z component squared is something other than 29. So let's start with A here, the 2, 4, 3. So if I go 2 squared plus 4 squared plus 3 squared, I get 29. So that the length of that vector would be root 29. Similar with B here, 5 squared plus negative 2 squared. I won't bother add 0 squared in because that's 0. So that's also the length of root of 29. And D here, see, it's the same numbers I used in A, except a couple of them are opposite signs. But negative 3 squared is the same as 3 squared. And negative 2 squared is 4, just like 2 squared is 4. So that will be also root 29. In C here, 16, 10, 3 is a lot longer than root 29. If we square 16 and add 10 squared and 3 squared, we get 365. So the magnitude of that vector would be root 365, so it's much longer. So that's why C would be the answer for question 2. Question 3, what's the magnitude of negative 3k? K is one of the unit vectors, the standard basis vectors. Remember, it goes I, j, k, so it's the one in the direction of the positive z-axis. It'd be the vector 0, 0, 1. And we multiply with negative 3, it would no longer be 1 unit long, it would be 3 units long. Now, it would be pointing down towards the negative z-axis instead of up, but it would be, well, it's negative 3k. Now, magnitude of vector is not negative, it's always positive. Excuse me. It's always positive. So we wouldn't answer C here, negative 3. It would be positive 3. So again, a vector 1 unit long multiplied by 3 or negative 3 is going to be 3 units long. So that's why A is the correct answer for question 3. For number 4, we're given these two vectors and asked to find the dot product of them. And so dot product, remember, we multiply the components and add them. So 6 times negative 1 would be negative 6. And then plus negative 4 times 3 would be, well, plus negative 12 or minus 12. And then 1 times 5 here would be 5. So negative 12 and negative 6, negative 12 add to negative 18. Plus 5 would be negative 13. That would be the correct answer. But notice there are no correct answers here. of the first 4 anyway. So 9's not correct. The dot product is a scalar. It couldn't be a point or a vector. And of course, 33 root 2 is not the same as negative 13. So we would answer E for question number 4. For question number 5, if D cross E is a 0 vector, then D and E are, and they're parallel. If you have parallel vectors, so let's say that's one vector, and I'm going to make another here, make a different color one. So let's say we had this vector here. They're parallel, they're supposed to be parallel. There's more than one way for me to draw a vector parallel to this. And it's a little bit difficult to see this maybe in two-dimensional, on a two-dimensional surface. Those two vectors, now those two vectors are actually are opposites, well, opposite in direction. But a cross product is supposed to be in three-dimensional space. So if you imagine a plane that goes through these, that's perpendicular to the screen or monitor you're looking at. It goes straight in from where you're looking, and any vector on that plane would be also perpendicular to the red and purple vector, the two vectors I drew at first, in case you happen to be colorblind. So there's not a unique direction for the cross product, and so that's why D cross E is the 0 vector. So if the cross product is 0, then the two vectors are parallel. For well, let's get rid of this here. This is not in the way of question 6. If B and C are perpendicular vectors, then the dot product is 0. That's dot product of 0 means that two vectors are perpendicular. Remember that now we're talking about B dot C. Then remember, this is the other formula for the dot product. And the only way, if they're perpendicular, the only way that can equal 0 is if this is 90 degrees. Because the cosine of 90 degrees is 0. So that's why a dot product of 0 means the two vectors are perpendicular. Last question, last multiple choice question here. If P cross B is this vector, then what's B cross P? So the opposite cross product is the opposite vector. So you need the opposite vector of this. So 47 would be negative 47, the negative 563y component would be positive 563, and the 219z component would be negative 219. So exactly the opposite vector. So B is correct for question number 7. In part 2, in number 1 here, it says illustrate the vector q, negative 3, 2, 5 on the diagram and make it look three-dimensional. So the way you make it look three-dimensional is you draw a box or prism around it. So remember, x comes out this way, y that way, and z is straight up and down. So kind of like x is coming out of the page towards you. The x component of negative 3 means we go 1, 2, 3 back here. And then the 2 is positive, so we go 1, 2 in the direction of the y. And then the 5 is positive, so we go 5 up. Okay, so that distance would be 5. So we're basically going here, here, and here. And so we draw a box around that. And so the box is supposed to make it look three-dimensional. So this up here would be the point negative 3, 2, 5. And so the vector that goes from the origin to that point would be the vector q, which is negative 3, 2, 5. And I might want my diagram up here for question number 2. Describe the axis or plane where each of the following points are located. Now, if you see two components that are both zeros, then it's on an axis. So 18, 0, 0. So that would mean that we would come 18 out in this direction and not go in the y at all and not go up or down at all. So we're still on the x-axis. Negative 2, 0, 0. So we would go 2 back here and then go nothing right or left for y and nothing up and down for z. So that's why those 2 points both lie on the x-axis. Negative 5, 9, 0. So we would go negative 5 and then up 9, and then but not off in the y direction at all. So that's still on the because you see it's z that's 0 here. That would still be on the xy plane because we went 5 that way and then Sorry, I think I did that wrong first. We would go 5 this way and then 9. We don't go up or down. The z component is 0. So, and similar with this one. Now, if you go 0, negative 4, 0, so 0, so nothing in the x direction, and we just go, well, 4 this way. So actually on that point's actually on the y-axis, but this one would be on the xy plane because we just went 5 that way and then 9 this way and nothing up or down. So this is on the xy plane and this is on the y-axis, so the 2 points are still on the xy plane. For question C here, 0, negative 8, 4, and 0, 7, negative 2. Notice the x coordinate in both those points is 0. So we will go negative 8 in the y and then 4 up. And so that's on the y-z plane. And then the same idea with this one here, because we don't go anything in the x. We just go, well, we go 7 in this case and then 2 down. So it's still on that xy plane. The plane that would be really on the surface of this page. That'd be the xy plane. And last one, 0, 2, 0, and 0, negative 15, 0. So zeros for both the x and z components for both. So that would be on the y-axis because basically, so we start here with a 0, 2, 0. We go 2 here, so that's on the y-axis. And for the 0, negative 15, 0, we just go 15 in that direction, so it's still on the y-axis. Question number 3. We're given these two vectors, a and b, and asked to determine negative 2b plus 6a. So negative 2 times the b vector here, plus 6 times the a vector. So I distribute the negative 2 in, so negative 2 times negative 3 is 6, negative 2 times 2 is negative 4, negative 2 times negative 1 is 2. And then 6 times 1 is 6, 6 times 4 is 24, and 6 times negative 5 is negative 30. And then I add the two vectors. 6 and 6 add to 12, so that's the x component. Negative 4 and 20, well, same as 24 minus 4, so it's 20. And 2 and negative 30 add negative 28. For b, 5a minus 3b, so 5 times vector a, so that's vector a, minus 3 times the b vector. So I distribute the 5 in here. And now, there's two ways you can do this. I just distributed 3 in and left this as subtraction. If you wanted to change that to a plus, you could distribute a negative 3 in. It will give you the same answer. So 3 times that's negative 9, 3 times that's 6, and 3 times negative 1 is negative 3. And so I'm now subtracting because I just distributed a positive 3 in. 5 minus negative 9, same as 5 plus 9, so that's 14. 20 minus 6 is 14, and negative 25, now subtract negative 3, the same as adding 3. So negative 25 plus 3 would be negative 22. For question number 4, 3 non-collinear points describe a plane in three-dimensional space, or R3. You're asked to explain how you could check that these 3 randomly chosen points were not collinear. Okay, we want 3 non-collinear points. So I've kind of got 2 examples here. The points A, C, and D are not collinear because they're not all in a straight line. So A, C, and D. Now, if we were to find the components of vector AC and AD, though you can see on the page that they're not parallel vectors. So we should find that those components are not multiples, or vectors AC and AD are not multiples. So AC would be the vector, okay, from A to C, so negative 10 minus 2 would be negative 12. 20 minus negative 4 is 20 plus 4 is 24. And 27 minus 7 would be 20. And now AD, so 5 take away 2 is 3. 9 take away negative 4, same as 9 plus 4 is 13. And negative 3 minus 7 would be negative 10. So there's the components, and you can see they're not multiples. You might look at the x and say, oh, that's negative 4 times 3. But if I multiply 13 by negative 4, I don't get 24. Or if I multiply negative 10 by that, I don't get 20. So they're not all in the same multiples. So AC and AD are not multiples. And I just noticed that I misspelled multiples. So there, we'll fix it. So AC and AD are not multiples. So points AC and D are not collinear. However, if you had 3 points that were collinear, like these three here, notice that they all follow a straight line, then you should find, for example, that AB and AC, or also BC, I didn't do BC, but they should all be multiples of one another. So AB, we would go -1 minus 2 is -3. 2 minus -4 is the same as 2 plus 4, that's 6. And 12 minus 7 is 5. And to do A and C, so -10 minus 2 would be -12. Oh, and I already did AC. I don't need to do that again. So that's AC. And we can see that they're multiples. This vector is 4 times this one. Now, -3 times 4 is -12. 6 times 4 is 24. And 5 times 4 is 20. So because A, B, and C are a collinear set of points, then vectors AB and AC, and also BC, should be multiples of one another. Question number 5. Determine the angle between the vectors C and M. And so we're going to use the dot product, the rearranged dot product, to find that. So cos theta is the dot product divided by the product of the two magnitudes. So we need the dot product of C and M. So -2 times -3 is 6. 7 times 0 is 0. And 4 times 3 is 12. 6 and 12 add 18. So that's my dot product in the numerator here. And I need the magnitudes of the two vectors. So -2 squared, and maybe we'll do this in the calculator here. So underneath the root here, it's -2 that we're squaring, plus 7 squared plus 4 squared. So we get the square root of 69 for the length of C, and then for M, so we're squaring -3. I won't bother to type in the 0 squared. They're both going to be 9 anyway, and 9 add 18. And so that's the magnitude of vector M. So my 18 goes here, root 69 times root 18. If I multiply 69 by 18, I get 1242. I guess I could do that here. 69 times 18. I would only rate that like that because then it's a little bit easier to do this calculation. So 18 divided by the square root of 1242. So it gives me 0.5107. Oh, a little rounding there. I see. I should have had a 7 there. Oh, no, it does round up. Okay, the 5 makes a 7 rounds to 8. I was looking at the 3 there. So 0.5108, so we take the inverse cos of 0.5108, which is about 59 degrees. I just round to the nearest degree. If you want it more accurate, you could do 59.3 or something like that. Question number 6. We're asked to prove algebraically that B cross C equals -C cross B. A lot of times in my proofs I'll say prove in 2 space or prove in 3 space. I don't need to do that here because the cross product is not defined in 2-dimensional space anyway. So this is going to be a 3-dimensional proof. So I'm going to call B the vector B1, B2, B3, and C the vector C1, C2, C3. Remember, use variables to represent the components, not specific values. If I called vector B, let's say the vector 2, 5, -4 or something like that, and see the same kind of thing, just with numbers, then that is only an example, it's not a proof. See, we're going to show that this is true no matter what B1, B2, B3, and C1, C2, C3 are. So I'm taking the cross, so I'm going to do B cross C first here from the left. So to do B cross C, I would go B2, B3, B2, B3, and then B1, B2, and the same with the C. So it'd be C2, C3, C1, C2, C2, C3, C1, C2. And so we do all this multiplying. So, excuse me, sorry for coughing in your ear. So B2, C3 minus the product of B3 and C2, so that's the X component, and then B3, C1, right there, minus B1, C3, that's the Y component, and then B1, C2 minus B2, C1. So that's the B cross C vector. So now we want to show that's the same as the negative of C cross B. So C cross B, I'm just going to put my C's on top and my B's on the bottom and this little symbol here to do the cross product. And so notice, okay, here's my I'm going to leave my negative up front until I distribute in the next line. So B3 gets multiplied by C2 minus B2 times C3, B2, C3, comma, and then B1 and C3 get multiplied. so B1C3 minus B3C1, B3C1. And then lastly, B2C1, so B2C1 minus B1C2. And I'm going to expand my -1 in here now, so everything just changes signs. All the signs change. And so I'm going to rewrite this with the positive first, so B2C3 minus B3C2, B3C1 minus B1C3, and then B1C2 minus B2C1, and this is exactly the same vector as up here. So therefore B cross C is equal to the negative of C cross B. So that's an example of an algebraic proof of vectors. Question number 7 has to find a vector perpendicular to Q and R. So similar to the last page, but we're working with numerical vectors here. I'm going to take the cross product of Q and R. So I'll write -7 and then the 2 and then 3 -7 on the end. And for the R, 0, 3, -5, 0, so 0, 3, -5, 0. And so -7 gets multiplied by 3 here first, and we're going to subtract from that the product of 0 and 2. So minus 0, 2, comma, and then 2 times -5 here, minus 3 times this 3 right here, and then 3 times the 0 right here, minus the product of -5 and -7, which is what's on the end here. So -7 times 3 is -21. Of course, minus this would be 0, so it's still -21. This would be -10 minus 9 would be -19. And this is 0, so it's really just -1 times -5 times -7, which would be -35. So that vector is perpendicular to both Q and R. That's one of the things we use the cross product for. Question number 8. I asked to find the area of the triangle formed by the points D, E, and F here. And so this is the triangle that we're finding the area of. So we actually would cut it off between here. And so this is the area we're finding. This kind of shading this in here. Now there's a reason I've drawn a completed parallelogram. Because we're going to use cross product here. The magnitude of the cross product of these two vectors is the same as the area of the entire parallelogram. But we want the triangle, which is half of it. So after I find the magnitude of the cross product, I'll have the area of this whole parallelogram, then we'll just take a half of it to get the area of the triangle. So that's why the whole parallelogram is drawn. So we need to find the components of two vectors that define sides of this parallelogram, like DE and DF, or I could do a little different. I guess I could have gone EF and ED and had my parallelogram come down here. It would give you the same value. So I'm doing DE and DF. So for DE, 0 minus 5 will be -5. And then -2 minus -1, same as -2 plus 1, so that's going to be -1. And 3 minus -4, same as 3 plus 4, so that's 7. And for the DF vector, so I'll go -6 minus 5, which is -11. 3 minus -1, same as 3 plus 1, so that's 4. And 7 take away -4, same as 7 plus 4, so that's 11. And so I'm going to take the cross product of those two vectors. So I'll start my little symbol down here, like I have previously. -1, 7, -5, -1. So -1, 7, -5, -1. And then 4, 11, -11, 4. So 4, 11, -11, 4. So we go -1 times 11 at the beginning here, minus the product of 4 and 7. And then that's the x component. And then 7 times -11 at the beginning here for the y, minus the product of 11 and -5. And then -5 times 4 minus the product of -11 and -1. So maybe we'll bring the calculator over here for this. So -1 times 11 will be, well, -11. And we're going to subtract 28 from that. So x component is -39. That would be -77. Now this would be plus 55. So -22 for the y component. And then that would be -20. And now that's 11, so just minus 11. So -31 for the z component. I guess I should have left the calculator here. So we're going to find the magnitude of this now. So the root of this squared plus this squared plus this squared. And so just to demonstrate all these values, So negative 39 squared. That's where the 1521 comes from. Negative 22 squared. Oh, I missed a 2. That's the 484. And negative 31 squared. 31 squared gives you 961. Of course, I could have just done this. You realize that the positive value gives the same square. So, a little quicker way to do it. So if we add 1521 and 484 and 961, we get 2966. So a half of that, a half of the root of 2966. And of course, if you want to know what that is a decimal, 2966, and then divide by 2. So about 27.23 units if you want that as a decimal. So that's the area of the triangle. Second last question here, number 9. Isaac is tightening the lug nuts on his ATV tires. The owner's manual suggests using a torque of 200 Newton meters to tighten them properly. And you're told that Isaac uses a 30 centimeter wrench and applies 600 newtons of force at an angle of 70 degrees. You're asked, what is the torque on the wrench? Are the lug nuts sufficiently torqued? Which means, is it safe? So this is the magnitude of torque. So the magnitude of R, that's the length of the wrench. So if we want it in Newton meters, I'll change my 30 centimeters into meters. So that'd be 0.30 meters. The magnitude of the force is 600 and the angle is 70. So we would take our calculator here. 0.3 times 600 times the sine of 70 degrees. So 169.1, so about 169 Newton meters. So that's the torque, but it's not enough because the owner's manual says you need 200 Newton meters. You need a little bit more. And of course, if you could apply a little more force, then he might be able to get there. But so let's assume that that's the maximum force that he's able to apply. Suggest ways he can increase the torque he is able to apply to torque his tires sufficiently. And it does say be very specific so we can achieve the necessary torque to tighten them and make it safe. So he could find a longer wrench, longer than 30 centimeters. Okay, and he could also apply it at an angle of 90 degrees because when this angle becomes 90, you see the sine of 70 is 0.9396, etc. But the sine of 90 is 1. So if you apply the force at a right angle, you get a larger torque. So it'd be a little over 6% higher. So Isaac could find a longer wrench or socket set and apply the force at an angle of 90 degrees to the wrench. So I have an example here. So for example, we found a 40 centimeter wrench and applied the force perpendicularly, so at a 90 degree angle. Then 40 centimeters, so 0.4 meters, 600 newtons times sine 90, that's 240 Newton meters. Now, you're not supposed to over torque stuff either because you can cause damage or make it more difficult to get it off next time. So that's more than enough torque. So he could actually reduce the force a bit to 500. And you see, if you did use that 40 centimeter wrench times 500 sine 90, you get the 200 Newton meters that are necessary. So that's some suggestions you could make to Isaac. Last question here, number 10. We're given a couple of vectors, m and v, and asked to find the projection of v onto m. So this is the formula for the projection of v onto m. And so we need the dot product of v and m. So negative 4 times negative 1 is 4, plus 2 times 3 is 12, 6, sorry. I'm thinking ahead here. Plus 1 times negative 2 is minus 2. So 4 and 6 is 10, minus 2 would be 8. So that's the dot product. And then we also need the length of vector m. So negative 4 squared plus 2 squared plus 1, that's 16, and 4 would be 20, plus 1 is 21. So the root of 21 is the length of vector m. So the dot product, the 8 goes in the numerator here, the length, magnitude of vector m goes in the denominator, and times vector m, the negative 4, 2, 1 vector. So root 21 squared is 21. So we're multiplying 8 21ths or firsts into this vector. So 8 times negative 4 is negative 32. So the x component would be negative 32 21sts. 8 times 2 is 16, so 16 21sts. And 8 21ths times 1 would be 8 21ths. So that would be the projection of v onto vector m. And that's the end of the tutorial, the test review.